Okay, so let's start. So welcome everybody to this exciting series of technical robotics seminars for this spring semester. So we are very much excited to organize these seminars second time at the Technion. Just a brief note what is expected in this semester. I don't know if you saw that. Wait, let me share my screen for a second. Wait. Dave, can you stop sharing for a few moments? Thank you. So the plan for this semester is to have 6-7 seminars. You can find all the info on this website that will be updated periodically, and hopefully we'll be recording all these seminars, and we'll post them on this website for you guys to be aware of. And with this, I'm very much excited to host this first time Dave, and I let Aviv to introduce him. Go ahead, Aviv.
Hi, everyone. So yeah, it's very exciting that we get to kick off the seminars with Dave Held from CMU. So Dave is an assistant professor at CMU. He's working on perception and control and robot learning. Dave did his PhD in Stanford and postdoc at Berkeley. Actually had the pleasure of sitting right next to him in my postdoc as well. And Dave recently got an NSF Career Award. He's doing super exciting work on robot learning. So I won't take any more of his time. Dave, the stage is yours.
Great, thanks so much. Thanks everyone for coming. So my name is David Held. I'm an assistant professor at Carnegie Mellon University. And today I'm going to talk about my research on perceptual robot learning. So if we think about what is a robot consists of typically a perception system that takes as input some sensor inputs and outputs some estimate of the state of the environment, and a planning and control system that outputs the actions that the robot should take. Now, typically, the people who work on the perception side are called vision researchers, and the people who work on the planning and control side are called robotics researchers. And the question that I'd like to ask is, can we build a better system by thinking about these parts together as perceptual robotics researchers? So to clarify, I don't mean that we should merge the perception and control modules necessarily. I just mean that we should be thinking about both of these parts together. So why do we need to think about perception and planning and control at the same time? So for example, why can't roboticists just use the output of a computer vision method? Well, if we think about what the goal of computer vision is, typically the goal is essentially to understand what is in an image. So here are some typical outputs of a computer vision system. So they try to find where the objects are in an image and identify what type of object it is. But on the other hand, the goal for robotics is typically to understand what will happen if a robot interacts with its environment. So a roboticist would want to know if a robot interacts with this crumpled towel, what will happen if it grasps it a certain way. So let's take a step back and ask the question a different way. Why does most current work focus on only perception or planning or control? So I think there's another reason for this, which is the underlying assumption that many roboticists have that one day our perception systems will be perfect, or maybe nearly perfect with some small Gaussian noise. So if you believe in that assumption, then a reasonable plan forward would be to build better perception systems, design planning methods assuming near perfect perception, connect the components, and hope for the best. Maybe one day we'll be able to just plug these things together and everything will work. And I think in the factory, this assumption is mostly true. Robots can know what to expect coming down the factory line in terms of what types of objects, what poses they will likely be in. But I think the assumption is mostly false for the cluttered environments in which we work and live, due to many factors that will inevitably always cause perceptual errors, such as occlusions, poor lighting, small objects, limited capacity perceptual modules, novel objects, and deformable objects. So the question that I am exploring with my research is how do we bridge this gap between imperfect perception and planning and control? So for example, suppose that we have this crumpled towel. How should we represent this object in order to enable a robot to appropriately grasp and fold the towel? There are many different representations that one can come up with, and they have different trade-offs in terms of how easy they are to learn or estimate from an image, how suitable they are for the task that the robot needs to accomplish. So my goal is to learn to manipulate novel, perceptually challenging and deformable objects. And this requires rethinking robot perception and control algorithms to handle these types of objects and manipulation tasks. So specifically today, I'm going to be talking about a few projects relating to deformable object manipulation. And then I'll talk about one project at the end about transparent and reflective objects. So I'll begin by describing my work on SoftGym, which is a benchmark for deformable object manipulation. And this work was led by my student Xingyu Lin, shown here. So the traditional paradigm that we see in machine learning is to train on a large image data set. We run a machine learning algorithm on this data set, and we output the predictions of our system. And large data sets have driven forward the progress in computer vision over the last decade. So here are a few example data sets that have been used: ImageNet, Cityscapes, which is segmented images of autonomous driving scenes, and at the bottom, Microsoft Coco, which shows segmented images of objects in the wild. And these data sets have really driven progress in computer vision. So ever since ImageNet came out, we've seen steady progress on this data set over time, which is caused by new advances in computer vision architectures. And in reinforcement learning, we've seen some amount of similar progress using locomotion data sets, or really simulators in this case. So here's the famous Majoko simulator, where various people have developed reinforcement learning algorithms. But what about deformable object manipulation? So here are 4 different papers on deformable object manipulation, and you can see that they each use different setups, they each evaluate on different tasks, and they use different robots. And this makes it hard to compare different algorithms and see if we're making progress, and also makes it hard for a newcomer to jump into the field and see how their method might compare to all of the existing methods. Now, deformable object manipulation is an important application. There's many uses for it. For example, robots could help with cooking, laundry folding, packaging, or manufacturing and repair. And deformable object manipulation is also very challenging. So some of the challenges for deformable object manipulation include the high dimensional state representation. So as opposed to rigid objects, where the pose of the object can be neatly defined by the object's position and orientation, so just 6 or 7 numbers. For deformable objects like a cloth, the configuration of the cloth is defined by position of all of the nodes. In a simulator, this would often be represented as a mesh grid with hundreds of vertices. In real life, it's closer to a continuous structure. So it's much higher dimensional. Deformable objects also have much more complex dynamics. So trying to predict how the object moves as the robot interacts with it is much more challenging. And there's also a lot of self-occlusion. So if you only have this partial view of a deformable object in this crumpled state, it's difficult to estimate the full configuration of the object just from this viewpoint, because you don't know what the state of the cloth is underneath the object surface that's visible to you. So in order to drive progress forward in deformable object manipulation research, we developed SoftGym, which is a deformable object manipulation benchmark that's built on top of NVIDIA Flex. And here you can see some of the tasks that we've developed. So transporting water without spilling, pouring water into another cup, straightening a rope from a crumpled configuration, folding a cloth, spreading a cloth, and flattening a cloth from a kind of a lifted up position. And we call these specific tasks soft, gym, medium. We also have more difficult versions of the task that we refer to as soft, gym, hard. And we also have a version of the task that involves a robot, which we call soft, gym, robot. And so soft gym is not just this set of tasks. So we also evaluate how realistic the simulator is. So here's a comparison where we take actions in the simulator on the left and also the real world on the right, and kind of just visually compare how similar the results are. And you can see from mostly visual inspection that the crumpled configuration of the cloth after a certain action is relatively similar on both sides. So this gives us confidence that this is a good benchmark to help us understand how a robot should perform deformable object manipulation. Okay, so we also evaluate the performance of different state-of-the-art algorithms on this task. So for each of these tasks, we compute a score that one is the maximum possible value of that any method can obtain. And here with this black line, I'm showing the performance of using the cross-entropy method if we allow the method to have access to the ground truth state and the ground truth dynamics of the environment. So this is kind of an oracle. In the real world, you don't have the ground truth state, ground truth dynamics, but if you did, this is how good of a job you could achieve. And these lines show the performance of various state-of-the-art methods that use mostly RGB information to try to perform the task. So, so there are some tasks that are easier than others. Transporting water without spilling is one of the easier tasks. Other tasks the robot can eventually do given a very large number of trials, such as pour water. There are other tasks such as spread cloth that even the best performing algorithms actually perform far below the ideal performance on this task. And so this motivates further research in this area. And we also are able, sorry, yes?
Is this evaluated always on the same type of cloth, or are you measuring generalization to different cloths? Or different
No, we're not even, for spread cloth, we're not even evaluating generalizations to different cloth. Yeah.
Thanks.
Great question. Okay, so we can also analyze the different methods to see how I'm trying to understand why they perform poorly. So just a visualization, here's the oracle that has access to ground truth state and ground truth dynamics, trying to perform this transport water task without spilling. And here is one of the RGB-based methods that's trying to perform this task. And you can see that it mostly transports most of the water, but actually a lot of it is does end up being spilled. Here's an example of, so in this case, the robot are these two flying spheres. And you can see, given ground truth state and dynamics, it can mostly flatten this cloth. But if we only have access to RGB information and apply the state-of-the-art method, the cloth is still very crumpled. And so why is that? So it's hard to exactly tell for model-free methods, but there are other methods that are model-based methods that actually work by trying to make predictions about the future. And we can visualize those predictions and see how good they are. So we took a state-of-the-art method called Planet, which learns dynamics in a latent space and chooses actions based on these latent dynamics. So here's a particular sequence of actions that was chosen by Planet, and you can see the ground truth outcome of those actions, which is that it spilled a lot of water while trying to pour it into a cup. And here below this are the predictions by Planet. And you can see that in the predictions, actually, most of the water all the water is poured successfully into the cup, and the predictions doesn't involve any spilling. Here's another example of the true outcome of a sequence of actions which are trying to fold the cloth, and you can see the cloth is still very crumpled. Below it, you can see the prediction of the latent dynamics model, and you can't really see the wrinkles. It might look to this model like the cloth is flat. And so basic takeaway that we got from this analysis is that latent vector dynamics might capture the overall motion of the object, but it loses subtle but important details. So for these deformable objects, spilling a few droplets out of the cup actually is important, even though it visually doesn't take up a lot of pixels, and similarly with wrinkles on the cloth. So this is sort of foreshadowing, but we will build on this insight in developing our method for this task. So the conclusion here is that SoftGym is a new set of benchmark environments for deformable object manipulation. Our benchmark should speed up research progress by allowing researchers to build on top of implemented methods for deformable object manipulation, test new methods, and easily compare it to previous methods. And we also analyze state-of-the-art approaches and try to understand why current methods fail on this task. So,
Dave, before you move on, can you talk about the complexity of simulating these operations?
Yeah, so NVIDIA Flex is actually a fairly efficient simulator. It simulates, it uses a GPU to simulate the motion of many particles in parallel. So it runs, I believe, it's faster. It's a little bit faster than real time, and you can kind of parallelize across different GPUs. So yeah, it's I would say compared to simulators that people typically use in graphics, it's less realistic, but much faster.
Much faster.
Great question.
Thanks.
Sure. Okay, so given those insights, I'll next talk about our work that we recently completed on model-based reinforcement learning for cloth manipulation. And this is work done by my students Yufei Wang and Qingyu Lin. So the question that we're going to explore in this work is how do we learn a dynamics model for cloth? So we want to be able to predict what effect a robot's actions will have on the cloth, even if we only get to observe the cloth in this crumpled configuration initially. So there's different types of dynamics models that you might construct. A very common one, which we saw in the previous project, is to learn a latent space dynamics model. So the way these methods will work is they take this image and pass it through an encoder, they output a latent vector, then they concatenate that with an action, pass that through a dynamics model to predict the next latent vector. And this is a very general approach. Latent vectors can, in theory, capture anything, but as we saw, it often loses important details, and essentially, we think this is because this structure doesn't capture any inductive bias about the cloth itself, and this allows it to easily overfit to the training data and not generalize to new scenarios. So another approach that's common that has been tried in the past is to learn a pixel dynamics model. So given an observation image, you can pass it through an encoder and a decoder and predict what the next image would look like after taking a given action. So this encodes a little bit more structure into the model because you're trying to predict the full image instead of just latent vector. But having an image or pixel-based dynamics model doesn't really capture the physical structure of the cloth. So in contrast to these approaches, our approach is to learn a graph dynamics model over the estimated cloth mesh. So at a very high level, we're going to take an observation point cloud, use that to estimate a mesh of the cloth at a given time, we will imagine the effect of a given action using a graph neural network dynamics model, which will then predict what the mesh will look like after the action is applied. So why is it a good idea to use a graph for this problem? Well, a graph actually pretty well can capture the underlying structure of the cloth. So a cloth is often modeled by a set of points connected by springs. And we also might need different edge types for modeling different forces. So for example, you might have edges to model the spring force between two nodes. You also have the gravity force to consider, and there's also collision forces if different parts of the cloth collide and kind of push each other. So that's a different kind of edge that we might model in the graph. And there's also friction between different parts of the cloth, or the cloth and the table. So, okay, so suppose that we want to model the cloth with a graph and learn graph dynamics. What are some challenges associated with doing that? So we're going to imagine we have an RGBD observation of the cloth, and then we extract from that a voxelized point cloud, and we're going to operate on the voxelized point cloud. So, so the first challenge is we don't know just from this observation how the points are connected on the underlying cloth mesh. So some of these points that we observe are directly connected to each other in the mesh. Some of them are just physically near to each other due to the way the cloth is folded, and we don't directly observe those connections. Secondly, we can't even see most of the mesh points on the cloth due to self-occlusions. We can only see the points that are visible to us. So how do we learn a mesh dynamics if we can't see the mesh and we can't even see the points? So our solution to this problem is we're going to first learn to estimate how the visible points on the cloth are connected. So just the points that are visible to us, we should be able to at least estimate how those might be connected to each other. And secondly, we're going to learn a dynamics model just over these visible points. We call this visible connectivity dynamics. And the basic idea here is that the dynamics model is going to learn to take into account the partial observability of the cloth. So it won't be directly a pure physics-based dynamics model. You can think of it more as an intuitive physics dynamics that's taking into account the partial observability. So here's an overview of our visible connectivity dynamics model. So we start with an RGBD observation of the cloth. We're not going to use color at all. We just take the point cloud and voxelize it. And then we'll take all nearby points and say that these points might interact with each other due to collisions or friction forces. So we connect any points that are nearby with collision edges. We then use what we call an edge prediction GNN to predict which points are actually connected to each other on the underlying cloth mesh. Then we pass the collision edges and mesh edges to our dynamics GNN, which will predict how the point cloud will deform in the next time step. And then we repeat to simulate the long-term effect of an action. So going into a little bit more detail, the points from the voxelized point cloud become the nodes of our graph. And we're going to connect all points that are within some radius r to each other via what we call collision edges. It's just an edge in the graph that has a label it's a collision edge. But it's supposed to represent collision forces. Specifically, and then once we have these collision edges, some of them will also be mesh edges, meaning some of these edges represent a connection between points that are actually connected on the underlying mesh. So in order to estimate which collision edges are mesh edges, we pass the collision edges through a GNN, and essentially we're solving a classification problem that we want to learn for each collision edge to predict whether it's also a mesh edge. So the input graph to the GNN is just on each edge, we have a feature which is the distance between the two endpoints, and that's pretty much it. Then you encode this graph, do message passing, decode it, and output a classification score, which is a number between 0 and 1 on each edge of whether this is a mesh edge or not a mesh edge. Okay.
If I may, so this way you basically avoid explicitly tracking the points from different frames.
Right. So so we just kind of on each time we get a new observation, we recompute we re-estimate the collision and mesh edges. Yeah, that's right. Yeah, great question. Okay, so next we can pass the collision and mesh edges into the dynamics GNN, which is going to predict the effect of the actions on how the point cloud will deform. So specifically, so our input will be the collision and mesh edges. So on each node, we have a feature which indicates the node velocity and whether this particle is being picked by the robot, because if it's picked, then its position should not be subject to all of these forces. It's mostly the robot that determines the position of the picked, whichever node is being picked and moved by the robot. And the features on the edges are, again, the distance between the two nodes that the edge connects, as well as an indicator of whether that edge is a collision edge or a mesh edge. And the output, we'll have a separate output for each node, which is the acceleration of this node for the next time step. And then we integrate the accelerations to get the predicted position of all of the nodes of the cloth. So in a little bit more detail of how we do planning with this model, so we're going to have the robot search over high-level pick and place actions, so pick a certain node and drag that node to a given location. However, it's difficult to simulate the effect of a large motion in a single time step. So we break that motion down into many small motions and use our dynamics model to simulate the effect of the action after each of these motions. But we only get an observation at before the pick, and then the rest of the steps are just a prediction of our model. So we're going to use a dynamics model to predict the position of the cloth at each of these waypoints. We typically use 100. For planning, we need to optimize search over actions to optimize a reward. In this case, we're going to focus on the cloth smoothing tasks. So we want to have a reward that estimates how smooth the cloth is. So to do this, we take the observation of the cloth and imagine a sphere at each point cloud and compute the total covered area of the spheres. And that's the reward. So we want to maximize this area. We're going to do a very simple greedy planning approach, so usually known as random shooting. So we will sample and pick and place actions, score each action according to the predicted reward based on our dynamics model, and then choose the best action. So very simple on that side. We train this in simulation using the SoftGem simulator that we talked about earlier. We will create a training data set for our edge GNN and dynamics GNN models just by taking random actions on the cloth. And we're going to do zero-shot transfer from sim to real, which in our case is pretty easy because we're operating on voxelized point clouds. So to transfer this to the real world, we take the real world point cloud, voxelize it the same way, and then the point cloud resolution will be the same between sim and real, and it transfers quite easily. Okay, so here are, I'm going to show the results. So before I hit play, just to describe what we're going to see here. So on the left is the crumpled cloth, and we'll see the robot taking actions to unfold the cloth. On the bottom right, we'll see the estimated graph. The green arrow is the action that the robot is going to take, and you'll see how we predict how the mesh will deform after the robot takes its action. On the top right, we'll see different actions that are being sampled by the robot, and green indicates that the robot thinks this will be a good action. Red indicates the robot thinks it will be a bad action based on the prediction from the dynamics model of how the cloth will deform after taking each of these actions. So the arrow indicates kind of the pick point, and the end of the arrow is a place point. Okay, so I'll play the video. So, okay, so I guess kind of talking through what we see here. So in the bottom right, we can see the mesh deforming, and then on the left, we see the robot taking the action. So you can kind of see the comparison between what the robot predicts will happen if it takes a given action and what actually happens. So the predictions, of course, are not perfect. The cloth in simulation is not exactly the same as the cloth in the real world, but it's sort of a good enough prediction to be able to mostly flatten the cloth. So here you can see kind of another sequence of actions that the robot performs to try to unfold the cloth. And I'll just skip ahead in interest of time. So here's, so that was a cotton cloth. And next we're gonna see a silk cloth. And these were both trained on this, these are both using the same dynamics model trained in simulation that is able to generalize these different cloth materials reasonably well. So the cloth doesn't end up perfectly flattened at the end of these, but it's sort of fairly flattened. And as we'll see later, it's doing a much better job compared to the baseline methods. So here's some more visualizations of the, this is visualizing the prediction of the mesh edges. So on the left, we can see the ground truth mesh edges. On the right, you can see the predicted mesh edges. So kind of by visual inspection, you can see there's kind of like this gap here between the different parts of the cloth, and we estimate the same gap. The colors are just for visualization purposes. We don't use color anywhere in our model, just the point cloud. Also note that the estimation of the mesh edges doesn't need to be perfect because the learned dynamics model can adapt to errors in the edge prediction. We also evaluate this quantitatively, so we can compare the initial area of the cloth compared to the current area, and we normalize by the maximum area. We compare to a pixel-based dynamics model, a latent vector dynamics model, and an RGB policy. These are three state-of-the-art methods on this task. They're all trained with more data than our method gets to train for to be really fair. And here you can see the performance. Our method is shown in blue. On the x-axis is the number of pick-and-place actions that each method is allowed to perform, and the y-axis is the normalized performance, with one being the best. So you can see even if each method is only allowed to perform 5 actions, our method does significantly better than the others. Given more actions, at least our method and VSF both improve and eventually converge to a mostly flat configuration, but our method given for any given number of actions allowed, our method results in a better performance. We also ablate different components of our system to see, do we need to learn the dynamics model instead of using a simulator? So here's the performance of our full system. Whereas if we don't learn the dynamics model and just use the simulated dynamics from the Flex NVIDIA simulator, we get significantly worse performance because our dynamics model is actually learning to account for the partial observability, whereas the simulator does not it assumes that the cloth is sort of fully observed. We also test whether we need to infer the mesh edges with various modifications of our method, and they also each do worse than the full system. So to conclude this section, we propose learning visible connectivity dynamics over the visible part of the cloth. Our graph-based dynamics model encodes a strong inductive bias that models the cloth physics, and our dynamics model learns to compensate for partial observability. and we demonstrated zero-shot symmetrical transfer for cloth smoothing of different materials. So that was my work on model-based reinforcement learning for cloth manipulation. And next, I'll go on to talk about our work on cloth grasping. So the problem here is, so suppose that we have this crumpled cloth, and instead of smoothing it, we just want to try to fold it directly. We kind of just want to grab the cloth on the edges or corners and kind of just directly flatten out the cloth. So how can we grasp the cloth at the true edges or corners? Note that some of the things that on this picture that might look like edges are actually just folds or wrinkles in the cloth. And if our goal is to flatten the cloth and fold it, we don't want to grasp at those locations. So how can we distinguish between true edges and folds or wrinkles? So previous work in this area would often perform a procedure that involves manipulating the cloth into a configuration from which perception is easy, and then folding the cloth from there. So kind of picking up the cloth, moving it around a little bit until you understand the cloth configuration, and then folding it. These methods can work eventually, but they are fairly slow. So how should we model the cloth to enable fast and accurate manipulation? So our method is we're going to take a semantic segmentation approach here. So given an input depth image, we will pass that through a segmentation network and output the heat maps that represent the locations of corners and edges of the cloth. The way we will obtain geometric labels for this is using a colored cloth with colored paint or tape that gives us the ground truth location of the corners and edges. Note though that our method only takes a depth image as input, so we don't get to see these colors at test time. They're only used to generate the ground truth labels for training. And we can put a loss between these. Now that's mostly sufficient, but there's sort of an issue when you actually try to grasp the cloth based on these edges, which is that you need to actually understand how the edge is oriented. So should you grasp this edge from this direction or from that direction? Just these edges on the heat map don't necessarily provide that full information. So in order to estimate grasp directionality, we add another output to the cloth, which is the inner edges. So here you can see we've painted in green an inner edge of the cloth. So now we have these three different outputs, and this will allow us to much better estimate the directionality of the edge for grasping. Okay, so let's go into a little bit more detail about grasping and some issues that might come up. So here's an estimated segmentation of a cloth that's folded a certain way, and you can see the estimated corners, outer edges, and inner edges. So let's zoom in on this part and think about this procedure. So where should we grasp the cloth? Well, suppose we want to grasp it at an outer edge. That's the yellow portion. Okay, so for example here. Now, what direction should we grasp it? So we sort of just described, do we want to grasp it based on the direction from the outer edge toward this nearest inner edge? So that's the direction from yellow to green. Now, the problem is, what about these arrows shown here? So the red arrows are connecting a yellow region to a green region, but they're not connecting the outer edge to its corresponding inner edge. This is a different inner edge of the cloth that's just nearby because of the way the cloth is folded. But if you try to grasp the cloth in this direction, you won't be very successful. So what we need to do is estimate directional uncertainty. The way we do this is by looking at the directional variation in a neighborhood of a given point. So say for this point, we take all points in the neighborhood and compute the direction from that point to the nearest inner edge. And you can see there's a lot of variation here. So this is a bad place to grasp. On the other hand, this point, if we look at a neighborhood in the direction, all the arrows are pointing in the same direction. So there's lower directional uncertainty. So here's a heat map of the directional uncertainties for each of the different locations. And so we're going to use this to determine where to grasp. So we'll grasp at a place that's an estimated edge that also has low directional uncertainty. We train with just 8 minutes of video. It's very easy to collect once we have this painted cloth. And here you can see the results. So here's a crumpled cloth. We're trying to estimate the cloth corners. You can see in the top right, we are segmenting the cloth, estimating grasp directions, directional uncertainty, and we use that to figure out where to grasp on the cloth. So here you can see some different visualizations of us grasping the cloth in all sorts of different ways. Here we're grasping cloth edges from different crumple configurations. And we also can generalize very easily to different colors and sizes of the cloth. So we generalize the colors because we only take as input the depth image, so we don't even see the colors. And we generalize the different sizes because our method is fully convolutional segmentation network, so it scales pretty well with the cloth size. We also estimate the importance of direction and uncertainty prediction. So the dashed blue bar shows the performance of our full method on some metric that we've defined for cloth edge grasping success. And if we don't estimate the direction, but just kind of choose the direction randomly, then we get a pretty big drop in the success rate. And if we estimate the direction, but don't estimate directional uncertainty, then we also get a substantial drop in the success rate. So both of these are important for the success of our system. So to summarize, our method distinguishes between true edges of the cloth and folds. We select a grasp based on estimated directional uncertainty, and we thereby achieve robust grasping of this crumpled cloth. Okay, so that was my work on cloth grasping. Just trying to check the time. So maybe I will actually just make sure that I get through the next project in enough time. I'm gonna jump to my work on transparent and reflective objects, but people who are meeting with me later can ask about my work on offline reinforced learning if I don't get through it. So, okay, so the work on transparent and reflective objects was work done by my student Thomas Wang. Okay, so if we look at grasping today, state-of-the-art grasping methods work pretty well on opaque objects. So here are some examples of grasping these opaque objects. This is pretty simple nowadays for robots to do. And that's because they use depth images to infer the object geometry. So here's using a Kinect depth camera, we're able to perceive the depth of these objects. But depth sensors don't typically work very well for transparent or specular objects. So depth sensors, in brief, work by projecting light onto the scene, and the state-of-the-art time-of-flight cameras measure how long it takes for this light to bounce back. And if you have a transparent object and the light goes through the object and hits the table, and we mostly measure the depth of the table. For specular objects, the light scatters in many different directions and also gives a noisy depth estimate. So as a result, state-of-the-art grasping methods fail on grasping transparent and reflective objects. So here you can see the state-of-the-art methods when being applied to these objects in this. So the depth sensor fails to really detect these objects, and as a result, the grasping performance is very poor. Now, previous work has tried to address this problem of transparent object grasping, but previous methods typically involve either a very large number of real-world grasp attempts, a high-fidelity simulator to simulate how depth objects might look in images, or many different viewpoints and specialized hardware. So as a result, these methods exhibit poor generalization to novel environments, or they can be very slow. In contrast, our method does not require any real grasp attempts, human labeling, specialized hardware, simulation of transparent objects, or multiple viewpoints. Our method only requires the following. One, a data set of 250 paired RGBD images of opaque objects. So these are just images that we collected in our lab of a bunch of objects that are opaque objects. And we have the image of these objects and the depth image of these objects. We also have the depth-based grasping network, that predicts a grasp score for each of the different possible grasps of these opaque objects. So for every possible kind of location this imagery might grasp and orientation, our method outputs a score of how successful a grasp would be. Not our method. This previous method that we're building on, the depth network, outputs a score for how successful this network thinks this grasp will be. And this network is known to work pretty well for opaque objects. This is the one we were showing earlier. So our insight for grasping transparent and reflective objects is that RGB is a better modality than depth for perceiving transparent and specular objects. So here on the left, you can see these objects, and you can perceive them pretty well in RGB. On the right are the same objects in a depth image, and the first row, the opaque objects, come out pretty visible, but the next rows are transparent and specular objects, and they're much more difficult to see. So how do we leverage this insight? First, we are going to take images of opaque objects. We put it on the table in our lab and record a depth image and an RGB image. We pass the depth image through the pre-trained depth-based grasping network, which outputs a set of grasp scores. So again, for every location in this image, it's outputting a score of how successful a grasp would be at that location and orientation. So this is the pre-trained depth-based grasping model. And then we have an RGB-based grasping model network that we're going to be training. And we train it with basically an imitation loss that we want to imitate the scores output by the depth-based grasping network. So we have this dense set of scores, again, for every location and orientation, and we want to have the RGB network imitate those scores. Then at test time, we're going to input a transparent object or specular object into the depth and RGB networks, and we're going to output a set of scores for every possible grasp. And now we're going to do the simplest thing that we can think of, which is just average the scores for each of the grasps. So averaging is obviously the simplest thing you could do. We originally had a lot of other ideas of how we might do this in a more complex way. But it turns out that this method actually works about as well as we could have hoped, as you'll see from our results later. So we didn't really see any reason to kind of improve it any further. So why does this work? Well, first, let's note that the depth-based grasping network does output a reasonable grasp prediction for the opaque objects used during training. The RGB network learns to imitate this depth network on opaque objects where the predictions are good. Then the RGB network is able to generalize this training to transparent or reflective objects, which look mostly similar to opaque objects in RGB, even though they look terrible when viewed with a depth sensor. And then we combine the output of both RGB and depth networks to help our method be robust to changes in visual texture, like background or lighting variations. Okay, so here's the set of objects we use for training. It's this collection of opaque objects. At test time, we test on a different set of opaque objects as well as transparent and specular objects. And here you can see a visualization of our results. So here's a cluttered pile of transparent objects, and I'll sort of just let this play for a little bit. So we go through and grasp each one. You can see most of the grasps are successful. Occasionally we'll have some failures. So our gripper, actually, it's a Sawyer gripper. If you use the Sawyer before, you'll know that it can't open very wide. So this bottle is actually almost too big for it, but from a certain angle, it is able to grasp the bottle. So we can actually just go through and clean up this pile pretty efficiently. Here's another case where we miss it once, but then grasp it successfully. And then here's kind of the last object that we eventually get. Okay, then here's kind of a similar thing for specular objects. So on the top left, you can see the depth readings for the specular objects. And you can see it's mostly a big hole where the specular objects are, because the depth sensor returns kind of just an invalid reading at these objects due to the way that the projected light reflects off of the objects. So, so as you watch this, you can see that actually the main failure cases are caused by objects that are kind of spinning around, which doesn't have anything to do with the fact that they're specular, it's just the shapes. So in terms of the task of handling specular objects, This is why we decided not to do anything more complex than the kind of method that we developed. We think that the remaining benefits to gain here are by reasoning about how to grasp spinning objects or using maybe a three-finger gripper. And I'm not going to play through this whole video, but we're able to successfully grasp opaque objects still as well. Remember, we're combining RGB and depth. So here you can see the quantitative performance of our method. So blue is the previous depth-only base grasping method. Our method is shown in red for opaque, transparent, and specular objects. And you can see that we significantly improve performance for transparent and specular. So to summarize this section, we train an RGB network to imitate a depth-based network on opaque objects. And then we combine depth and RGB networks for grasping opaque, transparent, and reflective objects. So that was my work on transparent and reflective objects. So I think maybe I will wrap up here just to talk about some future work that I'm interested in doing. I think there's a lot of still room to explore in terms of learning to manipulate challenging objects that are interesting from both the perception and the planning sides. So, so in this work, I mostly talked about deformable, transparent, and specular objects, but there's many other objects that have interesting properties and make them interesting for both perception and planning, such as dough or things that can be molded, mixtures of objects, other types of objects that can be folded, granular material, articulated objects, and objects that can change their form in other ways, such as squeezing a lemon or peeling a vegetable. So I'd like to acknowledge the students that worked on the projects that I described. Which one was the lead author of the offline reinforcement learning project that I didn't get a chance to talk about. Here I'd also like to acknowledge the different funding sources that funded the research that I was lucky to be able to do. With that, I will end here, and I'd be happy to take any questions that you might have.
Thanks a lot, Dave, for this exciting seminar. Okay, so we have time for questions. Who wants to ask? Just go away and ask.
Yeah, I have one question regarding the second topic you showed for the cloth manipulation. You showed how some actions are considered good by the robot and some are not. How were these actions generated?
Yeah, so they were actually just generated by random sampling. So we just sample a pick point on the surface of the cloth, and then a place point that's kind of just like a random rotation and magnitude away from that. Yeah.
Okay, thanks.
Sure.
More questions?
Yeah, I have a question. On the cloth manipulation, if I understood the methods correctly, there's a strong dependency on knowing the shape of the cloth in advance, right? It has to be rectangular because you simulate, the simulations work with a rectangular cloth, or on the grasping, the training cloth was rectangular. And my question is whether you've investigated how this would generalize to other shapes of cloth, or could this generalize, or do you have ideas on how to generalize this?
Yeah, that's a great question. So I guess I would say a few things. So first, for the graph-based cloth manipulation, we believe that it should be able to generalize pretty well to different shapes of the cloth. That's mostly because the operations that the graph neural network performs are local message passing operations. So it's passing sort of latent vectors between neighboring nodes of the cloth. So the graph doesn't really sort of see the global shape even. It sort of just sees like the local shape and then kind of passes messages to transmit information to different parts of the cloth. But the fundamental aspects of the cloth dynamics that it's learning should be fairly generalizable to different shapes, although further experiments will test whether that's true. For cloth grasping, we showed how it generalizes to different sizes of cloth. One thing that's kind of interesting actually is in terms of t-shirts, t-shirts don't really have edges in the same way that towels have, where there's like actually a border with a hem that creates kind of like a firm edge. T-shirts are kind of, if you think about it like topologically, it's more like a I mean, basically it kind of wraps around completely, right? So basically, so the method doesn't really generalize to that, and it's hard to even really define what you mean by cloth edges on a t-shirt. So I guess we have an intuitive sense of what it means, but defining it for an algorithm is a little bit of a different story. So so for that, I think we'd have to think more about how kind of what is the task that we want to accomplish and how we can reason over the different parts to accomplish that task. It's possible that with a training data it would still work, but it's a little bit of a tricky question for that reason.
Thanks, and thanks again for a great talk.
Sure.
Right. Some final questions for Dave? All right, so I think at this point we'll conclude.
Thank you.
Thanks a lot, Dave, for this great talk.
Sure.
Thanks a lot, and see you in 2 weeks for the next seminar. Thanks a lot.
Thanks.